Welcome to Calculus. Today we will investigate calculating the integral as signed area. We'll take a look at two examples. Our first example is the integration from x equals -2 to x equals 1 of the function 3x plus 4. And our task is to draw a graph of the signed area represented by this integral, and then we want to compute it using geometry. So let's graph our function 3x plus 4 over the restricted domain from -2 to 1. So that's a linear function with the y-intercept of 4. So we'll plot that y-intercept, and then the slope is 3. Again, I only want to extend this graph from 1 to -2, or from -2 to 1, however you want to look at it. So let's plot our second point for this linear function using that slope of 3. So I'm going to rise up 3 from the y-intercept 4, so that takes me to 7, and then I run 1. And that takes me to that right limit of the x interval. On the left side, we can extend it backwards. So if the slope is +3, if I'm headed to the left, I'll drop 3 from 4 to +1 and then run -1. That's equivalent to slope of 3. And then from -1, I can drop 3 more over to -2. And then I'm going to connect those points. This is the linear function, and we want to compute the integral. So again, we've talked about the integral indicating what's the area under the curve, between the curve and the x-axis. So on this part that's from, about -1 1/3 over to 1, that's definitely going to be positive area. However, on this left side, what's under the x-axis we would consider to be negative area. And so when we calculate the integral, it won't be adding those two regions together, but subtracting. I want to take the positive part that's indicated in the red and subtract from it the area that's indicated in the blue. Now, since these are just plain right triangles, we really can use a geometric formula to calculate the area. So let's set it up so that we connect it here with the integral. The integral from -2 to 1 of 3x plus 4 dx. So again, just remember those parts. This would indicate the height of a region, and this dx again is our width. As we saw with our limiting process, we're taking that dx down to smaller and smaller and smaller intervals. And what we'll say is that this is equal to the area of the upper triangle minus the area of that lower triangle that's below the x-axis. So let's remember the area formula for a right triangle. From geometry, we've got that that's half times the base times the height. And in fact, that's the same formula we'll use for each of these area representations. So the easy part for us to find is going to be the height. The height of this red triangle is going to be 7. So we'll start filling in what we know. So we got half times the base times the height we found was 7. Let's do the same for that blue triangle. So minus half times the base of that one times the height is definitely going to be 2. So what that leaves for us is the width or the base of each of these triangles. So I haven't put it in because it's crossing here at a fractional point on the x-axis. We saw that with our slope. If I went down 3 from 4, left 1, that takes me to -1, 1. And then down 3 over 1, it's crossing at some fractional mark. We can use our idea of slope here to help locate that coordinate. So if I've got a slope of 3 and I'm decreasing down and that first count out of the 3 hits the x-axis, it indicates to me that if that's a slope of 3 over 1, that these have to hit at thirds. So that point right there should be negative 4/3, comma 0. So the question is, can we check that? Is it possible to check that that's actually accurate? So really what we could do is plug in the x value into the function and see if it comes up with 0. So 3 times, we were saying that that looks like about 4. In fact, I should say negative 4/3. So just plug in that x value plus 4. And let's see if that results in 0. So the algebra has the 3's cancel, negative 4 plus 4, and that's supported by the algebra. So all that to say, the base of this red triangle with the positive area is going to be 2 1/3. I can represent that as a improper fraction 7/3. Now that we know that coordinate, we can also find the width or the base of this blue triangle that's below the x-axis. So it's from -2 to -4/3. So that's just a distance of 2/3. And now we can calculate. So I just need to multiply here. So I'm going to multiply my numerators. 1 times 7 times 7 is going to give me 49. Over 2 times 3 times understood 1 is 6. And then for my lower triangle, again, we're subtracting because it's got negative area, it's below the x-axis. I'll multiply the numerators here. 1 times 2 times 2 is 4. Over 2 times 3 is going to be 6 again. Those have the same denominator, so I can go ahead and calculate that. That's going to be 49 minus 4 is 45 over 6. And then definitely I can divide 3 as a factor out of both 45 and 6, and that's going to give me 15 over 2, or 7.5 units squared. In fact, we could use either the fraction or the decimal. And that computes the integral using geometry. Notice we didn't use any calculus to compute that. So that's a function that's given to us that's linear. And linear functions often give us triangular regions to calculate area between the line and the x-axis. But let's take a look at an example that involves a non-linear function. So here we're considering the integral from pi over 2 to 3 pi over 2 of sine of x dx. So this is definitely, it's a simple trig function. It's the sine function, and we're considering what is its integral if we're taking our restricted domain to be from pi over 2 to 3 pi over 2. So on our graph, that's a rather narrow interval in the domain. And somehow we've got to use geometry to deal with a nonlinear curve here. So let's plot what part of sine function exists between pi over 2 and 3 pi over 2. So we'll just create a small table here just so we can graph it. And again, I'll put pi over 2. See that pi is in between there. We could include a lot more values than these 3, but I think these 3 will give us what we need. So then let's calculate the output for sine of x. So we'll start with pi over 2. Sine of pi over 2, remember that's 90 degrees. And when I think sine is the vertical component divided by the radius. Well, at 90 degrees, those are identical. It's going to be a vertical component of 1 and a radius of 1. So it has the value of +1. We'll compute now sine of pi. So that's at 180 degrees. Again, the vertical component here in our numerator has changed. So at 90, it's a vertical component of 1. At 180, it's a vertical component of 0. It's purely horizontal. 0 divided by radius is always going to be 1, but that has the output of 0. And then let's check at sine of 3 pi over 2. So that's at 270 degrees. So we're going at 90. So 90, 180, 270 is the lower you can think of 90 degrees. Its vertical component is going to be -1. And the radius is always going to be 1. So we see that that's -1. So there's a nice symmetry here that we have to take advantage of. If I plot this sine function at pi over 2, it's 1, pi is 0, 3 pi over 2 is -1. And then I can sketch the sine function within that interval. And so I see it's very symmetrical. We have to use that idea here. As you can see, geometry would be very challenging to calculate that precise area because that boundary line is curved. And so we're really kind of faced with a conundrum about actually finding the precise or accurate area of each of those red and blue regions. But it turns out we don't have to, because if I think about this, the way that it's partitioned on the x-axis is that these regions are identical. And so what I'm really thinking here is that this is equal to the area of this left region. So we'll call it the region on the left, which is positive, minus the region on the right. But again, since they're identical regions, we see that symmetry in our table, but just different sign. The ultimate output is going to be 0. 0 units squared. And at the end of the day, we don't really have to calculate anything. We just have to notice that the regions have the same area, and then depend on the fact that the difference would be something minus itself. That's going to be 0. Thanks for joining for these 2 examples of calculating an integral using geometry. See you soon.